on this page, we focus on the same example that we focused on before, but now we're kind of zooming in more on the random assignment aspect rather than the direct control. So we're still talking about these surgeries for children with hernias, and we're seeing if random assignment using the applet really does randomly assign, well enough to make it so that age is no longer a confounding variable. So in this example, like we said, okay, they compared the recovery times for each type of surgery. There were two types, laparoscopic, I think I'm saying that right, and open repair. So here the explanatory variable is the treatment, which type of treatment they're going to get, which type of surgery, and the response variable is recovery time. So let's see. So let's consider one of these confounding variables, age. We kind of talked about this in the applet below, same applet. We're going to randomly generate two different treatment groups out of these 48 students, children. So as before, doctors are trying to control the influence of age on recovery time, trying to make sure that this is not a confounding variable. So that if the recovery time for one type of surgery seems like less than the other type, we can say that it's because the surgery type is better rather than it's because the children were of an older age or a younger age, and that's why they recovered more quickly. So one way they can do it as researchers, they could try to use direct control. So for example, researchers might use only 10-year-old children in the experiment, but as we said in the last page, that's not really feasible always because there probably aren't that many enough 10-year-old children that have to have this surgery to make this a good experiment. So in this case, since direct control won't work because, there aren't enough children of that age that need the surgery, we use random assignment to control the effects of age. So let's talk about what random assignment is. We kind of showed that there's a dot plot of the ages of the 48 children with hernias who participated in this experiment. Looks like a large portion of them are around 9 years old. See if you could see this. Let's see this. Oops, sorry. There we go. That kind of vertical line. It has 1, 2, 3, 4, 5, 6, 7, 8. It looks like dots in it. So the most children are in the 9-year-old age group, but the ages range from 4 over here to 13 over here. And then the mean, which is basically the average of all these ages, is a little over 8 years old, 8.29 years old. Okay, so we kind of talked about that in the previous page. We're going to try to use an applet to randomly assign 48 children and see if the mean, when we randomly assign, does it really seem like that it's randomly assigning to where the mean for the first treatment group, age-wise, is about the same as the mean for the total age group. So we had talked about with that dot plot above that the mean or the average age for these 48 children altogether is 8.29. But when we randomly assign them to the two groups, we want to make sure that the average age for group 1 that's getting one treatment versus the other is about the same. And of course, that's kind of relative. When I say about the same, it's like, okay, what does that mean? But I guess just to where it seems close enough to where no one would say, oh, well, these children were younger and these children were older, so no wonder the surgery worked, that kind of thing. So the applet, it looks like it's starting here on the treatment 1, the first type of surgery. They took half the children and assigned them to this first treatment. The mean or the average age is 8.24, which is pretty close to the mean above in the kind of turquoise circle. That's pretty good. And then treatment 2, the remaining children were put in treatment 2. The mean or the average age of them is 8.35. That's pretty good. I think to me those are very close to 8.29, to where I don't think we could say, we could say that age is no longer a confounding variable. But maybe we'll randomly assign a couple more times and see how it goes. Let's try one more time here. So now the average age for treatment group 1 is 8.56, which is still a little higher than it was before, but still pretty close to the mean above here. And then the treatment 2 group, the average age is exactly 8 years old, which is a little younger, but not too far below. I think we'll try it one more time and see what we think. Well, that looks pretty close. Yeah. Look at that. The mean for treatment 1 group is 8.32, which is very close. It's only 0.03 units away from being the mean of the overall. And then the second treatment group, 8.26, which is also only 0.03 units away from being the same as the mean for the overall group of students. Or why do I keep saying students? Children. Oh my gosh. I'm losing it. Anyway, so do you feel like this random assignment's actually working? Does it feel like it's actually random, and random enough to where you wouldn't maybe blame age for being a factor? It wouldn't be a confounding variable? I don't know, it seems like it's similar, but maybe we'll see what their thoughts are. Click here for our conclusion. Okay, let's see what their conclusion is. Wait for it. Okay. The results will vary. Okay, so they're saying that this is what they did when they clicked on the random assignment. They got first this one here. Treatment 1, the mean, I think our means were closer to the total mean of 8.29, but theirs, they got 7.88 for treatment 1 and then 8.71. Those are still pretty close to the total mean for 8.29. They did it once again. Let's see. And they got the two means for each treatment group, 8.3 and 8.25. That seems very close, very, very close to the mean of the overall group of children. Don't say students again, right? And then apparently they did it one last time, a third time. Here we go. Oh, now you can't see it. There. But the first mean was 8.46, the second 8.13. So it does seem like it's pretty random. I mean, I think when they say random, they really mean random. So with random assignment to treatment groups, doctors can assume that the differences they observe in recovery times are due to the treatment type and not due to the influence of age on recovery time. Okay. So it does seem like the treatment groups are similar age. That way, any differences we see in the response variable are due to the differences in treatments. That way, random assignment controls the impact of confounding variables. Random assignment in an experiment eliminates confounding, just as random selection in a survey eliminates bias. Yeah. And then in this comment, they make a comment about how you could randomly assign. You could put every child's name in a hat, but that seems, I don't know, kind of more difficult than it has to be. The first 24 names drawn get the first experiment. The rest of the children get the second experiment. Or you could flip a coin so that heads means the child is assigned to the first treatment, and of course tails means they're assigned to the second treatment. But if you think about it, this method that could create groups with slightly different sizes. Because what if you flip a coin 48 times and you happen to get more heads than tails, or vice versa? But that would be fine, I guess they're saying, because we're not really, I guess we're looking for averages here. Even though there are more children getting one treatment rather than the other, we're still going to average their recovery times. So the number of children in each treatment group wouldn't really matter, I mean, as long as they're sort of in the same ballpark.